So we're gonna do the slideshow here. Okay, so there we go. And so now we're talking about quantum mechanics, which is in section 7.5 of the textbook. So quantum mechanics is super complicated, and a detailed study of this is beyond the scope of this course. You run into it if you're a chemistry major in senior year or a physics major, maybe a little bit sooner. But for right now, for Chem 200, we just have to kind of know what are the results? What did quantum mechanics tell us? And remember, the idea of quantum mechanics is that the big picture is that matter has wave-particle duality. So we're going to take electrons and think of them as waves instead of just particles. And when you do that, and you do a whole bunch of math, and we'll show you some of the equations that you use. And again, I highly encourage you to watch some of the other YouTube videos to get a little bit deeper understanding of this, picture it. But some of the results are what I just said. Matter, like electrons, has wave properties as well as particle properties. We can't say exactly where an electron is. We can't, that's why orbits don't work. So an orbit is something where you can predict exactly where the electron is. It's like on a path. We can't do that in quantum mechanics tells us that that is not possible. It's not that we don't have enough information or that someday we'll be able to, period, we cannot do it. It's not allowed by rules of nature. Something called the Heisenberg uncertainty principle, which is mentioned in the other video. We can only look at its most probable locations, where it most likely is to be found. We can take those probabilities, which are equations, and graph them. So we can have the equation of probability. So if you have an electron, it has a certain energy. And when it has that specific quantized energy, it has a very specific equation that tells us where it most likely is. And we can graph those equations and look at them. And those probability graphs are what we now call orbitals. So Bohr called his very narrow path orbits. And they decided, sort of in honor of that, to say, well, those aren't really true. They're not following a path, but we're going to say where the electron most likely is. It's like more like a volume, an area or volume of a space it can be in, a three-dimensional space, as opposed to a path. We're going to call them orbitals. And orbitals tell us where we can find an electron with a certain energy about 95% of the time. Sometimes you'll hear 90%. About the same idea. 90 or 95% gives you pretty much the same graph. Don't worry about the percentage exactly. All right, so up at the top here, I threw something up there. Don't worry, you don't have to know that, okay? But I just wanted you to see it. It's called Schrodinger's equation, and that's the equation that has to be solved to get these probabilities, to get these wave functions of electrons. So you say, hey, I think an electron behaves like a wave. Now, we're not saying that the particle itself moves on a wavy pattern. We're saying the electron itself or its probabilities can be modeled as waves. And that's the big equation you have to solve there. I'm not going to go into all the details. If you're interested, some of the other videos I posted talk a little bit more in detail about it. Not crazy detail, but a little bit more. I will point out here that this guy here is the Greek letter psi, P-S-I, and that is the wave function or the electron as a wave that we're looking for. And if these are partial derivatives, so in calculus, so this is differential equations, partial differential equations that has to be solved. When you solve this, for hydrogen, okay, so you can solve this for hydrogen. It has one electron and one proton, and you can solve it. And these are some of what you get for some of those psi, some of those wave functions. And if you see here, see how this says 1s? So this is the equation for the well, not quite the orbital, but the wave function of a 1s electron. In order to get the orbital itself, you have to square this because the probabilities of where the electron are happen to be the wave function squared. So if I square this and graph it, that's what an orbital is. looks kind of weird because over here we had X's and Y's and Z's, and we don't have that X's and Y's and Z's anymore. Because it turns out it's easier to actually do this in something called spherical coordinates, which is instead of X, Y's, and D's, you have R's and thetas and phi's. It's a different coordinate system. You don't have to know it, but this gets high level math here. But either way, you can graph the square of this and give your 1s orbital. Similarly here, this is a 2s orbital for hydrogen. And if I square that, I get the orbital. Here's a 2p orbital of hydrogen. If I square it, I get the orbital. So it's not the orbital yet, but if I square it, I get the orbital. And down here, we have the other two 2p orbitals of hydrogen that if I square that, I get that. I get the orbital itself. Now, hydrogen's electron in the ground state would be in the 1s, but we can energetically excite it to the 2s, etc. So that's why these would be empty in the ground state, but they are there because if you put some energy in, the hydrogen electrons will go up. Electron, I should say, will go up. You can tell that if you look at the line spectra from hydrogen. The line spectra is literally as the electron comes back down from a high energy state to the second energy level, you see these lines. Okay. All right, so when we graph these, about 90 to 95% of the time, we get something like this. And this is a graph where it's a little bit more detailed than you're normally going to see. So this is a 1s orbital of hydrogen. And the way that they've graphed it is that the higher the probability it is to find the electron, the deeper the color. So you have a really high probability of finding this hydrogen electron here. The nucleus would be right there in the center of the 0, point of this axis. So high probability close to the nucleus, and as you go farther and farther away from the nucleus, it kind of gets less and less probable finding the electron. So that's what the probability looks like. Usually what we do is, instead of drawing it with this sort of probability getting less and less as you go out, is we kind of simplify this and say, well, it's a sphere around the nucleus. 95% of the time it's found in this sphere around the nucleus. So that's why we get the s orbitals being spherical. So here's some more s orbitals. All s orbitals are spherical as n increases. So as you go from 1s to 2s to 3s, the orbitals get larger. For right now, where it says n equals 1, L equals 0 here, don't worry about the L. We're going to get to that at the end of this set of notes. But for right now, don't worry about that. It is just showing the 1s, the 2s, the 3s. So as the n increases, the orbital gets bigger. And this is like a slice. So imagine this is a three-dimensional sphere, and you've sliced it down the middle, and you're looking at a cross-section. Okay? As n increases, the number of nodes increases. So the node is this area here where it's 0. There's nothing there. By 0, I mean it's all white. So if you think of this blue area as the probability of finding the electron, it shows us that in a 2s, there's probability near the nucleus. And then there's another area of probability out here with no probability of finding it in this sort of in-between space. We call that a node. So this is not the 1s orbital inside the 2s. This whole thing is the 2s. And here's the 3s. It's got an area of probability, missing area, area of probability, missing area, area of probability. The area where there's no probability of finding the electron is called a node, okay, a node. What this is down here, these graphs here, are graphs of the probability, that's what this is, the wave function squared for a 1s, a 2s, a 3s for hydrogen, graph versus r, and r is the radius, the distance from the nucleus. So it shows us that, you can't see it, but it actually, at the nucleus, there's no probability of finding the electron. But when you get pretty close to the nucleus, there's a high probability, and then it drops off as you go. This would be going farther away from the nucleus. In a 2s, there's a high probability close to the nucleus, and then a 0 probability, which is right here, and then a little bit more probability, and then it goes back down almost to 0. And you can see for the third 3s that would happen too. So the nodes are areas where there's no probability of finding the electron. It sounds kind of weird that the electron can be here or here, and it can actually go from one spot to the other without passing through here. That's because you're thinking of electrons as particles. And in this case, they're modeled as if they were waves. And waves, if you think of a wave, if I could draw a wave like with my pointer here, there would be areas where it was a 0. Okay, like if I think of this as almost like a wave, right? A wave right here. And there's areas where the wave is 0, where it goes down and it's 0. It doesn't mean it doesn't exist. It just means that it has no amplitude there. So that's kind of what's happening with the electron. And again, in the other videos I posted, you might see some pictures of that might help. Okay, this is again what I just said, what a node is. Okay. For s orbitals, the number of nodes is always given by n minus 1. So 3s has 2 nodes, 2s has 1 node, 1s has 0 nodes, 5s would have 4 nodes, etc. So the next slide, we're going to look at these probability density graphs are kind of strange looking, and what does this all mean? Well, if you look at, imagine you have a tree, and it's an apple tree. And then your apples are ripe and they start to fall. And on a particular days, you come and look at the apples. And then you count and you find how many apples are in this first ring, this second ring, the third ring. And so what you would find is, as you have the distance away from the tree, the trunk of the tree, so the trunk of the tree is like the nucleus and the apples are like where you could find an electron. At a certain distance from the nucleus, you're going to have, right at the nucleus, right at the tree trunk, you can't find any electrons inside the trunk. But as you go farther away, you're going to have more apples. And then as you go even farther, it's going to fall off and you're going to have less and less apples out here. Now that would depend on the tree, what this would look like. So sometimes if you have a tree, you might have like dead space in the middle and maybe this would be farther out for a different tree. Okay? Younger tree might be closer in. So, but it gives you the idea of what this probability density graph is about. Okay, so that gives us, we talked about s orbitals, and that, remember, these are graphs of probability of where to find an electron with a particular energy. And so we looked at the s orbitals, the p orbitals, every p sublevel. So we have a 2p, a 3p, a 4p. All of them each have 3 orbitals. We know that from before. We call them px, py, pz, and they're kind of dumbbell shaped, or they have 2 lobes, sometimes we say it. And I'm getting down to the picture here. And they lie along the x, here's x, okay, the x-axis, the y-axis, or the z-axis. So that's px, py, pz. This is a little bit more of a graph with the probability density graphed in, where it's higher probability here, and then as you go farther away from the axis, less probability. As n increases from 2p to 3p to 4p, they have the same shape, but they get bigger, and then they're going to have nodes. All p orbitals have a node at the nucleus. So right here, there's no probability of finding an electron in this area near the nucleus. This is what they would look like if you combined them all on top of each other, because they really are, because the nucleus is in the center. D and F orbitals have different shapes. I'm just going to put this up here. So the d orbitals, most of them have 4 lobes, so kind of like a 4-leaf clover. They're just oriented differently on the axis. So remember, the nucleus is right in the center, and all of these are really right on top of each other. We're just separating them to see better. So they're in different planes of what we'd say. So this is in the YZ plane, this is in the ZX plane, etc. These 2 are in the same plane. They're just, this one is, the lobes are between the axes, and this one is right on the axes. And then we have this guy here, and I call this one the donut one. So it's like a donut. Now all of these have names. You don't have to know them. You know, b, x squared, y squared, etc. But you don't have to know those names. I'm not gonna. But if you see the labels, that's what they are. The F, it gets really crazy. Your book has even a little bit different shapes than this one. I've seen it 2 different versions. They have more, they all have more lobes. You have this double, these are both like double donut ones here. But they do get more lobes. And of course, we know that the F doesn't even come into play until you get into like the 4th energy level. This is just a cool picture I got off the internet. You can find it in various sites. And this is showing a different way to represent orbitals, instead of, in that one we looked at where the s orbital, where I said there was more blue where it was closer to the, where there was higher probability of finding the electron. What these people did is they graphed it. So these are all just graphs, computer generated graphs. We're not seeing the orbital here. We're just looking at a graph, because remember, this is where the electron is likely to be found. And what they do here is the brighter it is, the more likely it is for that electron to be found there. And right in the center is always the nucleus. So this is the 1s orbital, little tiny thing, brightest, very close to the nucleus. 2s, we have very bright, close to the nucleus. Then there's a node, and then there's more area where you can find it outside the nucleus, but it kind of diminishes as you get farther away. Here's the 2p. Most of it is right close to the nucleus, but this line going through it here, that's the node where you can't find it at the nucleus. Here's the 3s. It has 2 nodes. Here's the 3p. So it has that node at the nucleus. It also has this other node here. So it's got this bright area where you mostly can find it here. And then there's this area with less probability, but still significant out here. And here's one of the 3d. So this would be one. These are, there's other 2p and 3p orbitals are just representing one of them here. Here's one of the 3d orbitals. It has 2 nodes. That's why it has those 4 areas of probability. So that's a cool way to look at it. Okay, quantum numbers. All right, so there's another video out there that I posted on this, and he does a pretty good job explaining it. So you should, this is a confusing topic. You should probably look at both videos, mine and his, so you get this right. Okay, so we're gonna take a look at it. Now, where does quantum numbers come from? Well, when you do those mathematical equations, the ones I showed you, and I said these are the results of the Schrodinger equation, had all this crazy stuff in it. And I said, if you right in the beginning of this video here, I said, if you square it, it's the probability. What comes out of the math of this is that each electron, excuse me, in an atom has 4 unique quantum numbers that designate its energy level. So these numbers come right out of the math. So there's 4 quantum numbers designate the energy level of the electron. You can almost think of it as an address for the electron, but what I want you to understand is that these were not something that we made up, like, oh, we'll call it this, we'll call it that. These are how the numbers are, how they go from, some of them go from 1 to 4, some of them go from 0. We didn't make up how these numbers go. They came out of the nature of this mathematical calculation. They're part of the equations. Okay, so we gave them names, of course, but they are all part of the math. And so we gave them the letter designations N, L, M sub L, and M sub S. We usually use a cursive L because a regular printed L looks like a 1, so you're going to usually see a cursive L. So we're going to go through them one at a time. N is called the principal quantum number, and its allowed values, what it can be, are 1, 2, 3, up to infinity, pretty much. And that designates the energy level itself. We've already worked with N. We looked at N because N is the same quantum number that Bohr used. He didn't realize it, but basically Bohr discovered the principal quantum number. So if you do those equations, which says delta E is equal to negative 2.18 10 to the minus 18 joules, 1 over N final squared, 1 over N initial squared, that one, that's N, the N in there is the energy level of the electron when it makes these jumps. That's the principal quantum number. So Bohr discovered the principal quantum number. He didn't know it. He called it N though. He did call it N. So it's just the energy level. It's at the first, the second, and the third. So that was our first level of quantization, that this electron can have a level, the first, the second, the third level. Of course, we eventually found out there's sublevels. And L designates that sublevel. It's called the angular momentum quantum number, L. Its allowed values, what it can be, starts counting at 0. The maximum it can be for any specific electron is N minus 1. So you can have L go all the way up to whatever, 1,000, whatever. You don't see that though. Usually we only go up to about 4. But the allowed value for a specific energy level is that it can be up to maximum N minus 1. This causes a lot of confusion because sometimes students think that means L equals N minus 1. No, it can have values from 0 up maximum n minus 1. These are one of these things where once we start doing them, you'll understand it better. Okay, this is a little confusing when you first explain it. This is going to designate what we now call the sublevel. So for S sublevels, L is 0. For a P sublevel, L is 1. For a D, L is 2. For an F, L is 3. So you're like, why do we have to have a different way of saying S? Why can't we just say S? Well, remember, these are the numbers that are actually put into the mathematical equations. And so that they come out of those. So the S, the P, the D, and the F were sort of shorthands for this. So the quantum numbers came first before the S, the P, the D, and the F in terms of how we named them. Okay, the next quantum number is called the magnetic quantum number, M sub L. It has allowed values from negative L through positive L. So if L is 2, it goes from negative 2, negative 1, 0, positive 1, positive 2, negative L to positive L. We'll show you that in a minute. It's going to tell us exactly which orbital it is in the sublevel. So it's a label for each orbital. So we'll show you that in a little bit. Well, for example, the P sublevel, Px could be negative 1, Py would be the 0, Pz would have M sub L equal to positive 1. Okay. Then we have the spin quantum number. And the spin is that we say that the electron has a spin of plus 1/2 or minus 1/2. Those are the allowed values for spin. Spin is a really difficult concept to understand. We'll talk a little bit about it for electrons, but electrons aren't only ones that have spin. All particles, protons, and stuff have spin. And so we'll talk about that a little bit for electrons, but not go into major detail. But it is the fourth quantum number. If the electron is spin up, we call it positive 1/2. If it's spin down, we call it negative 1/2. So those are all the quantum numbers. I'm going to do we're going to talk a little bit about spin, but then we're going to talk about some examples. Okay. This is a table from your book, and it is showing you all the quantum numbers that are there for the first 4 energy levels. So when n equals 1, the only thing L can be is a 0. And we'll talk about, I'll remind you why that is in a minute. It's because we said L can go up to n minus 1. That's the 1s orbital. The ms, L is 0, and there's 1 orbital there. Now, what's kind of interesting is if you go down here to the 2p, and I'll talk about this on paper in a second. In the 2p, L is 1, because that's what we said. L is 0 when you have an s orbital, 1 when you have a p orbital, 2 when you have a d orbital. But M sub L has allowed values from negative L to positive L. So negative 1, 0, positive 1. You notice there's 3 values here. There are 3 orbitals. The reason we know that how do we know there's 3 p orbitals? Well, because there's 3 equations. All the orbitals are equations. There's 3 equations because you are allowed to have values of negative 1, 0, and positive 1 for M sub L. That gives us 3 equations for the p orbitals. So the reason we started out by telling you back in Chem 152 and reviewing it in Chem 200, there's 1 s orbitals, there's 3 p orbitals, there's 5 d orbitals, there's 7 f orbitals. We just said, yeah, that's what it is. But those actually are represented by equations. Every one of those is an equation, and every one of those equations has a different M sub L value. So the reason we know that there are this many 7 f orbitals is because there are 7 values of M sub L. Quantum numbers are going to tell us other things too. It's going to, in a minute, I'll show you how we know there was no 1p orbital or 2d or 3f because of the quantum number. So everything that you know about how many orbitals of a certain type and how many electrons in an orbital all comes out of quantum number. So we've already told you a lot of the results of the quantum numbers, even back in Chem 152, but we didn't really talk about the quantum numbers themselves. This is just reminding us what spin is. You can think of an electron as a little magnet, and magnets have a north and a south end. A charged particle, the reason they called it spinning is because a charged particle, like an electron that spins, would have magnetic properties, and it would have a north pole and a south pole. And if we're spinning one way, counterclockwise, the north would be up here. If it was spinning the other way, north would be down here. You don't have to know all that. So when you measure stuff with electrons, it turns out they behave like little magnets. What actually is true is the opposite. Magnets are really behaving like big electrons in their magnetic properties. We're not talking about magnetic properties in Chem 200, but it's cool to look up what paramagnetic and diamagnetic and ferromagnetic means if you're interested in that. But the refrigerator magnets you have, what's going on there is all their electron spins are lined up in the same way. So it kind of magnifies having this property. So kind of cool. I'm not gonna quiz you on that, but spin up 1/2, down 1/2 is what we need right now. Okay, Pauli's exclusion principle says no two electrons in the same atom can have the same set of 4 quantum numbers. This comes out of the math. It's not like you just made this up out of nowhere. But what's happening is therefore what the quantum numbers are doing. If you take any electron in a particular atom, you can give it 4 quantum numbers. So in a way, you could think of it as the electron's address or its ID number, because it's unique to that electron in that atom. Now, if you go to the atom next door, if you have 2 atoms next to each other, it's going to have electrons with those same quantum numbers. So it's not unique like a social security number is for everyone. But within an atom, every electron has to have a set of 4 quantum numbers while it has that energy level. Now, if that electron jumps to a higher energy level, it now has new quantum numbers. So it isn't like assigned to it forever. The quantum numbers change because the quantum numbers are really not designating the electron, they're designating the energy level of the electron. So if it changes energy level, sort of like if you move to a new house, you have a new address. So address is probably the better way of looking at it. So there's only 2 electrons per orbital and they must have opposite spins. That's Pauli's exclusion principle. So we're going to look at helium. Helium only has 2 electrons, period. 1, 2, that's it. The quantum numbers of those 2 electrons in the ground state would be given in this table. So the electron configuration of helium in the ground state would be, I'm going to write it over here, would be 1s2. So when you do quantum numbers, it kind of helps to have the 2 things. First, it helps to have the electron configuration written out. Because you could think of this as sort of translating. You already know quantum numbers, just don't realize it. You know it in terms of 1s2, 2s2, etc. We're going to kind of translate it. Only the problem is the electron configuration doesn't give you every quantum number. It only tells you n and l. In order to get the m sub l and the m sub s, besides a quantum number, it's a good idea to write out a orbital diagram. So we're going to write out the orbital diagram here and get my, oops, sorry, that went faster than I wanted to. Oh no, went too far here. Hold on, go back up. I hit the wrong button. Go back here. Okay. Sorry about that. So helium, 1s2. And its orbital diagram, that's where we put the electrons in with arrows. We have, this is the 1s orbital. We could use a line or a box to represent it. And it has 2 electrons in it. And we're going to say, well, 1 has to be spin up and 1 has to be spin down. So this is a super simple one, but we're going to look at how we would then do the quantum numbers for those 2 electrons. So both electrons are in the 1s orbital. And as we've just indicated, and so therefore their n value is going to be both 1. So see this one here? That's always n. If you don't get n right, if you write this down and don't get at least the n value right, you've missed the whole point. Okay, so n is always this. I'm going to kind of connect them there. N comes from this number here, okay? That's n. Okay, L is going to come from the sublevels. So we're saying that these electrons are both in an s sublevel, And so therefore, what we said, if you remember what we said before a slide or so ago, we said that for L, L equals 0 anytime you're in an s orbital, okay? L equals 1 anytime you're in a p orbital or a p sublevel, okay? It equals 2 for the d sub, any d sublevel, doesn't matter if it's which d, 4d, 5d, doesn't matter. And it equals 3 anytime the electron is in an f sublevel. So if you just remember that L starts counting from 0. Now, over here, what we have is L, because we're in the S sublevel, so the L must be 0. M sub L tells us which orbital it is. And M sub L has allowed values. The maximum and minimum it can be is negative L to positive L. Well, if L is 0, then M sub L must be 0, because negative 0 up to positive 0 is still 0. So this 0 and this 0 doesn't mean like nothing. It doesn't mean it has no energy. It's just like an address. So if you have a 0 at the end of your address, if your address was 100 something, whatever street, it doesn't mean your house isn't there. It just means it's the first one. So it ends in a 0. So that's what this 0 is. It's telling us that this orbital is the 0 orbital. So let me, something here. So this orbital in the 1s is labeled 0, okay? 0, that's what that 0 is, okay? I'll just go take this L and bring it over here and say that's the S that we got it from. Okay, and then we have these guys here, the M sub S values, and there's 2 of them. There's positive 1/2 and there's negative 1/2, because we have 2 electrons in this orbital and one is spin up and one is spin down. So so this guy here, this first electron, these are its 4 quantum numbers, okay? That's its address. So this one over here with the up spin, its address is 100 plus 1/2. The one with the down spin is 100 minus 1/2. So Pauli's exclusion principle has been followed, because it says that you can only have a maximum of 2 electrons in an orbital. They have to have opposite spins and they have to have their own set of 4 quantum numbers. So if you have 2 electrons in the same orbital, okay, anytime you have 2 electrons paired in an orbital, these first 3 quantum numbers are going to be the same. So these first 3 quantum numbers, it's like it gets you to the house that they're in. It's the N energy level 1, the sublevel 0, and it's the 0 in this case orbital. So this tells you which orbital they're in. Then this one tells you, well, which electron is it in that orbital. So we're going to do more on paper. I'm going to help you assign the quantum numbers to all the electrons in the ground state of carbon, and then we'll try the valence electrons of arsenic, and then I'll talk a little bit about different other kind of questions that can be asked with this. So I'm going to switch over. Okay, give me a second here. Hopefully this works this time. There we go. Okay, so we're going to look at the quantum numbers for the electrons of carbon. And we're going to look at all the electrons in carbon. It doesn't have that many. When you get up to 20, 18 electrons, you don't want to do this. But for carbon, it doesn't have that many. So I'm going to put a periodic table down here. Periodic table, and we see that carbon is over here. It has 4 valence electrons because it's in group 4, but it has 6 total electrons. 6 total electrons. And right now we're going to do the quantum numbers for all 6 of those. You don't always have to do all 6. It depends on how the question is asked. In this case, we said, let's do all of them. There's only 6. I like to first set this up. The best way to set this up is to do what you know about the electrons of carbon, and that is its electron configuration. I don't think we need the periodic table over here. 1s2, 2s2, 2p2. That's pretty easy. I think you know how to do that by now. The orbital diagram will help a lot. You can do it horizontally or vertically. Horizontally is fine. So the 1s, there's the 2 electrons. the 2s, there's the 2 electrons, and the 2p. And we only have 2 electrons in the 2p, so we're going to go like that, okay? So that's going to help us with these quantum numbers. So the next thing I'm going to do is I'm going to make a chart like I did before, where I have N, L, M sub L, and M sub S. And there are 6 electrons, so I'm going to just say electron here. Which electron are we focused on? Kind of go like this. Okay, so let's look at the electrons first that are represented by the one. You don't have to have this column here; it's not required, but it kind of helps me keep track of what's going on. So the 1s electrons, there are 2 of them. Both of them have n equal to 1 because that's what this one here is about. That's n. Both of them have L equal to 0 because remember what I said a little while ago was that for L, S is equal to 0, P is equal to 1, D is equal to 2, etc. Okay? So since we're in the S, so 1s, this tells us here, 1s. M sub L tells us which orbital we're in. So M sub L has allowed values from negative L through 0 up to positive L. Those are the possible M sub L's we can have. Well, if L is 0, the only possible value of M sub L is 0 because there's no negative 0 or positive 0. So since L is 0, M sub L is 0. This is the pattern you'll always see for an s orbital, n, 0, 0. And then since there's 2 of them, one is positive 1/2, one is negative 1/2. So that's the s orbital pattern that you're always going to see. Let's do the same thing for the 2s orbitals. They're going to be exactly the same, except the n is now 2. So this whole pattern is going to be the same. 2, 0, 0, plus 1/2. 2, 0, 0, minus 1/2. Okay, so that's pretty easy. Now we're going to look at the 2p orbitals. It's the 2p. There's 2 of them still in this atom. So n is still 2. Okay, n is still 2 because it's 2p. But now L has changed because now we're here. Okay, for L value for a p sublevel is 1. So those are going to both be 1s. They're both in a p sublevel. The M sub L tells you which orbital it is. Now for the s orbitals, there was only 1 orbital. So this was the 0 orbital. This was the 0 orbital. There's only 1. It's labeled 0. For the p, we go from negative L to positive L. So p, L is 1. So for p, we go negative 1, 0, positive 1 as the possibles. Those are the orbital labels, negative 1, 0, positive 1. X, Y, and Z was how we labeled them just sort of by letters. These are more than letters. So these aren't just numbers. These are part of the equation. So that's where these come from. So the way we have it drawn, we have 1 electron in the negative 1 M sub L and another one in the 0. So I'm going to write that down. Okay. Now, it turns out that all of these are the same energy. So writing it as negative 1, 0, positive 1 is not the only way to do it. I could have this electron here. I could have this one here. It doesn't matter which 2 they're in. The only thing that matters is they should both have the same spin. Turns out that's the lowest energy. So there's a rule somewhere that says if you have unpaired electrons, so these are paired, if you have unpaired electrons in a sublevel, the lowest energy state is when you have them have the same spin. It's called having parallel spins. Now, when you get to more, so if we had 4, 1, 2, 3, 4, you got to start pairing them up. But before that, you keep them parallel. But there's nothing that says they have to be in these 2. All these are equivalent, like identical triplets. But make it easy on yourself and go this way, negative 1, 0, positive 1, perfectly good set. So the other thing is I wrote them both as spin up. So I'm going to kind of put that here. But there's no rule they both have to be spin up. They could both be spin down. Doesn't matter up or down which one you write first. But again, make it easier on yourself. Turns out that if you had a bunch of carbon atoms that were free in the gas phase, they weren't bonded to each other or bonded to other things, half of them would have 2 spin up and the other half would have 2 spin down, just how it is. Now, what I get people doing sometimes that's wrong when I move up here is instead of writing a -1 and a 0 here, they write all of them. They write -1, comma 0, comma +1. They write this in the box or whatever this little table is. Only one of them here. I don't want to know, when we ask you to give the quantum numbers for the electrons, we don't want to know all the possible values it could have. That's like saying you could live anywhere in this house on the street. We want to know a good set, okay? So don't give me all 3 of them here. Don't write plus and minus 1/2. You have to give a full set. You see what we have here now? Is we have 1, 2, 3, 4, 5, 6 sets of 4 numbers, and those are sets of quantum numbers in carbon. It is true that over here, there's more than one possible right answer. It would be okay if this was a +1, for example. It would be okay if this was a +1, or if you had -1, +1, or 0, positive. Those are okay, but you don't write all of them in here, okay? It would also be okay if both of these were -1/2. I'm telling you that not because I want to confuse you or that I want you to write them different ways. You don't get more points for writing them, quote, creatively. It's because if you get a problem where it says, is this set of quantum numbers okay? Is this correct? You should know that, yeah, those are correct too. So that over here, we just took this and we translated into this. And what it tells us is each of these orbitals has its own sort of address. It's really an energy address. So I could go to this electron here and say, which electron is that? And in this way, we'd have to say, well, it's the down electron in the 2s orbital. Okay, got to kind of describe it that way. Over here, we can say it's the 200 -1/2 electron. So this is the sort of easier way of doing it. But the numbers are really about the equations. It's the 200 -1/2 energy equation. That makes sense. Okay, so we're going to do one more of these. Some more paper here. Hold on, I get a piece of paper. Oh, that'll work. Do that one. All right, so the other one in the packet that was suggested was to give the quantum numbers for the valence electrons of arsenic. Valence electrons of arsenic. You might not even know what arsenic is, but let's find it on the periodic table. It's over here. This is arsenic right here, AS. Now it's asking for the valence electrons. Arsenic has 33 electrons. We don't want to do 33 sets of numbers, but so we have to know what the valence electrons are. So if the valence, so let's do the electron configuration of arsenic, okay? On this periodic table right here. So we would go to, hold on, sorry. Here it is, okay. So we would go to the last noble gas before arsenic, which is argon, right? And we would write argon. And then we'd start counting from argon. So then we'd come over here to potassium, and that's 4. So 4s2. And then we hit the 3D, go all the way through zinc, 3d10. And then now we're in the 4p block, 1, 2, 3. Okay, 4p3. So they want the valence electrons of arsenic. The valence electrons are the outermost electrons, is probably how you learned it, but it's really the electrons with the highest N value, okay? That's these. Those are the valence electrons. So I've asked people to do this on a test, and sometimes they try to do all of these with the Ds. You don't have to do the Ds. Those aren't valence. They have the 3, the highest N value. And sometimes on a test, people only do these 3 because they think it's the last ones. No, it's the ones with the highest N value. Both of these have N equals 4. All of those are valence electrons. So we're going to do the quantum numbers for 4s2, 4p3. 4s2, 4p3, quantum numbers. Once again, I'd say we want to do the orbital diagram. It really helps a lot. So there's 4s, there's 2 electrons, there's 4p, and now we have 3 electrons. Okay, so though we have 5 electrons that are we're going to do this chart for. So I'm going to do the same chart that I did before. So let's look at those 4 s electrons. This should be pretty easy. The s has that pattern, only now our n is 4. So see how that's the same pattern? We've seen this pattern 3 times now. We saw it in helium, we saw it in carbon, and now we're seeing it in arsenic. Now we'll look at those 4 p electrons. There's 3 of them. Their n value is all 4 because they're all p electrons. Because they're p electrons, their L value is all 1. So 4, 1 is just a way of saying it's the 4p electron. Their m sub L value depends on the orbital it's in. We a little while ago said the orbitals for the p sublevel go -1, 0, +1. Now we have 1 electron in each. So what I was saying before about carbon, where it's oh, you could write it in different, this could be a 0 or a 1. These you have no choice, okay? There's 1 in each one. So you gotta have them -1, 0, +1. You don't write the plus, that's okay. I've seen people get this wrong because they start to say -1, negative, they put more, they write the same number more than once. And that would tell me that they were paired up, and you gotta remember they're not paired up yet. And in this case, they're all spin up. So again, if they were all spin down, that would be okay. But I get people also making the mistake of saying, oh, plus minus. So they'll go plus minus, plus minus, plus minus, and they're not. All of these, sorry, my screen froze there for a second. I'll come back. Positive, 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 okay? You can't say plus minus. So that would be the valence electrons of arsenic and their quantum numbers. Another way I've asked this question is to say, well, give me all of the electrons outside the noble gas core of a particular element. So then that would include possibly d electrons because they aren't in the noble gas core. Lots of different ways to ask these questions. Other ways that quantum number questions are asked is just sort of general. Okay, well, if I have an electron that is in the 5d, what are the quantum numbers that are associated with 5d? Well, n is equal to 1. I'm sorry, n is equal to 5. Where's my brain? And d is now equal to, if you remember so sorry about that. N is equal to 5. L for d is then equal to 2 because we said it goes 0, 1, 2, 3, S, P, D, F. So this is the 5d electron. What about m sub L? What about m sub S? Well, you're only asking 5d. You're not asking for the rest of the address. So that's all you can say about that. The other thing, the way these questions are asked is we give you a set and we say, is this right or wrong? Is this a possible set of 4 quantum numbers? And if not, why? What's wrong with it? So you could say something like 4, 1, -2, +1/2. Is that a possible set? Well, the answer is no. And the reason is if L equals 1, M sub L is either -1, 0, or +1. Can't be a 2, -2. So yeah, you can look at that. And try one more of those, like why is this not, oh, I'm gonna leave that there in case you wanted to copy that or something. Give you a second. Going kind of fast, so those 2 problems. Okay, so you can always pause the screen and copy it too, right? Rewind, we're on video. So another way, another thing that you could say is, let's say we had another example like that. Let's say I said this is a set. Could you have, let's say 2, 3, -3, +1/2. So N, L. The problem here is the L value because L can go from 0 maximum to n-1. So if n equals 2, L can be 0 or 1. It can't be 3. So that's why. let's look at those again. Those possible values and what they tell us about the atom. So we said that N can go 1, 2, 3. That's its allowed value. Just keep counting up. L starts at 0, 1, 2. Maximum is N minus 1. M sub L is negative L to up to 0, up to positive L. And M sub S is easy, plus 1/2 or minus 1/2 for an electron. What's interesting about this is, I was kind of talking about this a little bit on that table that I showed you. If you look at, for example, this guy, N equals 2. Okay, let's look at that. If N equals 2, L can still have a 0, or L can be 1, because that's the maximum, N minus 1. So let's translate that. L equals 0 is an s orbital. L equals 1 is a p orbital. So that tells us we are allowed to have a 2s of 2p, right? There's no 2d. Why is there no 2d? Well, because we told you. But the real reason there's no 2d is because of this. The maximum you can have is n minus 1. That's this one here, that's the reason that we have 1s, we have 2s, 2p, we have 3s, 3p, 3d, etc. The reason for those allowed sublevels is this n minus 1 is the maximum. This tells us how many orbitals we have. S equals 1 orbital. P equals 3 orbitals. D equals 5 orbitals. That comes from M sub L. So everything, and this is the 2 electrons per orbital. 2 electrons per orbital. So all the things we told you on the first day of this, and we were still meeting face to face, okay, when I said, here's some review of Chem 152, all those rules you learned about orbitals and electrons come from these quantum numbers. The quantum number rules, which we didn't make the rules up, nature did. When we did the math, they came out of it. Just that we can't show you the math right now because it's too complicated. All right, so we're almost done.